Hi, this is Jack Simons at the University of Utah. In these series of videos, I'm going to talk about the wonderful world of molecular anions. But before getting into the material, I want to give you some information about some sites that I think you'll find useful. So this is my home page, simons.hec.utah.edu, showing me. And first is this link that is the 2012 and later websites for theoretical chemistry and molecular anions. So on that link, I'm going to collect a lot of other materials about molecular anions. That's an ongoing thing. But also on my home page, if we scroll down a bit, there's a thing called Molecular Anions website. This is a website that I created several years ago that lists a lot of material about people and the subjects that they're studying in the world of molecular anions. You can see the faces and stories of lots of people who do research, experimental and theoretical, studying molecular anions. So I think you'll find that to be a very valuable source of information. Now let me go on now to this material that I prepared that I call The Wonderful World of Molecular Anions. So this is a photograph showing myself and my wife and several of our faculty colleagues and their children in the Wind River Mountains of Wyoming. Let me start now by just telling you a little bit about my own history in studying molecular anions. In 1970, Carl Lineberger carried out the first direct measurement of an electron affinity of an atom. It was actually by detaching an electron from the S- anion to produce the sulfur atom. So he carried out the first direct measurement of an electron affinity of an atom in the gas phase. In 1971, I joined the University of Utah faculty, and I was interested in studying something that was difficult and that other people hadn't studied before. So by 1975, there were still only 19 atoms that had their electron affinities determined by these laser detachment experiments. By 1985, it had grown to 40, and by 2002, more than 1,100 species, atoms and molecules, had electron affinities determined by this method. So in the early 1970s, I became interested in the challenge of studying negative ions theoretically, because I knew they were being started to study them experimentally. So in 1972, I just want to point out something that's a little bit of a difficulty here for the experimentalists and the theoreticians to compete with one another. In 1972, it was very difficult to calculate, using the Schrodinger equation, the energies of an anion and a neutral atom, let alone a molecule, to within an electron, a tenth of an electron volt. That is, to get the energy difference within a tenth of an eV was very difficult. The experiments, though, like in Lineberger's experiment of the detachment of the C- anion to form the C atom, the electron affinity was determined to a precision that was awesome, several decimals into the electron volt fractions. So the experimentalists were way ahead of us in terms of accuracy, but we still needed to make some progress, and so we tried to. So in 1973, my postdoc Wes Smith and I were the first developers of what we call the equation of motion method for treating electron affinities of small molecules and atoms. And one of the things important about this is that we were able to compute these electron affinities directly, which means we were not calculating, for example, the energy of C- and the energy of C and subtracting the two, but we were actually calculating the intensive quantity, the electron affinity, as the number that comes out of our calculation. And these developments in the 1970s that we carried out actually, I think, were somewhat pioneering, because they allowed people to start making progress in computing and understanding atomic and molecular anions and electron affinities. And then throughout the 70s and 80s and all the way to 2010, my coworkers and I actually did a fair amount of studies of different kinds of molecular anions that I'll be talking with you about here in this series. And my goal here is to sort of show you the members of this family of molecular anions, so you can see that they're not just boring things, they're very interesting, and they have somewhat novel and I think surprising properties to them. So let's now talk a little bit about why anions might be special, in the sense that they're not qualitatively the same as a cation or a neutral molecule. And on this picture here, what I'm trying to do is to illustrate the potential energy experienced by an electron as it approaches the valence, and as it approaches from the asymptotic region and into the valence regions of cations, neutrals, and anions. So, for example, in this fuchsia color down here, I have a picture that I think would be representative of an electron approaching a cation or a neutral molecule. So suppose you were an electron in a water molecule and you're very far away from the water molecule in one of those lone pair orbitals maybe, and you want to know what's the potential energy that you feel due to the underlying structure of those 2 protons and the nucleus of charge 8 and the 9 other electrons. And the key is that you feel an attractive potential at long range, because at long range that H2O plus cation is sitting back there pulling on you. You're the 10th electron. So at long range there's an attractive potential. The other thing that's important is that attractive potential has a 1 over R shape to it. For the H2O case I was talking about, it would be minus 1 E squared over R. If you were instead talking about, for example, an electron in a water cation, so you're the 9th electron, and there's only 8 other ones inside of you, as well as this nucleus of charge 8 and the 2 protons sitting there too, then it would be minus 2 E squared over R, because you would feel an underlying effective charge of 2 pulling on you, because it's a monocation that you're involved in there. In any event, there's an attractive potential. That's what's important. And the other thing that's important is that attractive potentials form this 1 over R attractive shape to it, and the fact that that 1 over R persists until you reach a distance where the other electrons start to push you away. That's where the repulsions occur in here. So this distance is characteristic of the valence sizes of the occupied valence orbitals of that molecule. And the bottom line is that for most atoms and molecules, this attractive long-range Coulombic potential and then shorter range inner shell electron repulsions is deep enough to give rise to many bound electronic states. So for example, this line right here would represent the lowest energy state of that 10th electron in the water molecule. This would represent, this would represent the energy of that same 10th electron, but in an excited state in that water molecule. And this would represent the next excited state and the next. But the key thing is that most neutral molecules have a very large number of electronically bound excited states. And that gives rise to the possibility of carrying out electronic spectroscopy experiments on the neutral molecule from its ground state to excited state, ground state to other excited state, and so forth. Now, if you were a singly charged anion, suppose, for example, you were OH minus, there's qualitatively a difference, because if you're the 10th electron in OH minus and you're far away from the underlying proton and nucleus of charge 8 and the other 9 electrons in there, then at very long distance you don't feel a Coulomb potential attracting you, because you're the 10th electron and there's a nucleus of charge 8, a nucleus of charge 1, and there's 9 other electrons inside of you, so there's no net Coulombic attraction, no net charge pulling you. So at long range there is not this long range 1 over R attractive potential. The longest range potential actually is the interaction of U with the dipole moment of the molecule, the so-called charged dipole interaction, and that varies as 1 over R squared. So I illustrate that here with this red curve, showing that it comes in at shorter ranges, and I also show it as giving rise to a net potential that is not as deep as the Coulomb thing, because most molecules don't have large enough dipole moments to make this potential drop extremely deeply before the inner shell repulsions again turn on and cause you to get repelled by the other electrons in the molecule. So for most molecules, even with dipole moments up in the 10 and 20 dBi range, which are very large, this potential is shorter range because it's a 1 over R squared and not as deep as in the case of the neutral molecule or cation case. So the bottom line is that molecular anions, monoanions, have at long range an attractive potential that is 1 over R squared, charged dipole. Of course, they have also charged quadrupole, charge-induced dipole, polarizability potentials that contribute also. But the longest range part is this 1 over R squared. And for most molecules that have laboratory, realizable dipole moments, the depth of this potential well, and this is very important, the depth of the potential well is so shallow that usually only one, if any, bound electronic state exists. So in the case of molecular anions, say OH minus, this would represent the energy of the electron in that outermost last orbital of OH minus, and it is bound, that is, it's lower than asymptotically where the electron is free, but there's not an excited red line here because there's no bound excited electronic state of OH minus. So most molecules, most molecular anions, monoanions, have really only one bound electronic state. They can have larger if the dipole moments are higher. They can have more than one, but it's very rare to have more than one bound electronic state. That makes the experimental study of molecular anions, electronic study, very difficult because there aren't bound states where you can do bound-to-bound transitions and look for vibrational progressions and all that kind of Frank Condon information. So the electronic spectroscopy of molecular anions is a completely different kettle of fish. And finally on this introductory slide here, I've shown one other potential here, this blue. And this would be the kind of potential one would experience, for example, if you were in a dianion or a trianion, a multiply charged anion. So suppose that you were an electron in the sulfate anion. So you are that second negative charge, if you will. When you're very far away from the underlying sulfate monoanion, you know, the SO4 minus 1, and then you're the minus 2, when you're very far away and you approach that anion, you actually first feel a repulsion because you now feel the SO4 minus 1 pushing you away. So the multiply charged anions have asymptotically repulsive potentials, and then as the electron approaches and gets into the range where the valence electrons and the valence orbitals are available to attract it, it can have an attractive potential that's due to the electron being in that, say, that lone pair orbital on one of the oxygen atoms of the sulfate, and that potential can be deep enough to maybe have an electronically bound state, but if a potential isn't strongly enough attractive, it may not even have a state that lies below zero. So multiply charged anions may or may not have bound electronic states, and that's what we're going to be seeing now in some examples. So let's start to look at some examples of these